Hi everyone, this is Mr. Cervone. Welcome to my math channel. In today's logic lesson, we will be learning about indirect proofs. Assume that as a student, you walk around and you find a note that has been ripped, as shown in the figure here. And on the note it says, tonight's Yankee game has been canceled. The game will be made up on whatever month, 31st, 2020. Now we don't know what month it is. So the do now states, assuming the original date of the game was August 5th and the Yankees don't play any game after October 2nd, 2020, what is the date of the makeup game? So how will we solve this? So here we have to actually come up with certain assumptions. So we have to somehow come up with months until December and then make a decision if it actually works or not. So let's list all these months. So let's assume that the month here is November. So let me write this in, November. Okay, so is that possible that this could be November? Well, the answer is no, okay? So let me actually write this on the side as well. So here we have November. So what's wrong with this month? Well, it's not possible for November to have a 31 of November. So November doesn't have 31 days, but only 30 days. So if we assume that this is November, then we have some type of contradiction. Okay, and the contradiction is in the days of November, okay? So let's continue further now. Let's assume that this could be October. Okay, so let me write this here. So this is our assumption now, October. So October does have 31 days. But what's wrong with that? Well, according to the do now, it says that Yankees don't play any game after October 2nd. So the fact that here we have October 2nd and here we have October 31st, that is also a contradiction. So let me write this, contradiction. Okay. So now let's continue and let's assume now September. Okay, so would September work? So let me write this here, September. Does that work? The answer is no, because again, we do not have 31 days in September, only 30 days. So here we also have another contradiction. Okay, it contradicts with the number of days in September. So now we're going to write August. And would August work? Well, it says here that the original date of the game was August 5th, right? And they don't play any games after October. So obviously we have October and November contradicting because they don't play any games after October 2nd. Plus September because we don't have 30 days. We only have 30 days in September. So the only one that works is actually August, okay? Now, the answer is August here. This example is a demonstration of an indirect proof. How so? Because it turns out that in logic and in an indirect proof, you're stating the opposite of the conclusion, and then you're forcing a contradiction. And that is basically the definition of an indirect proof. So here's the definition. An indirect proof is an approach in which you assume the opposite of the conclusion and force a contradiction. Now, how can we say that we did that in the do now? Well, if you go back here, so here we're assuming the opposite of the conclusion of August. What's the opposite of August within those constraints between August and October? We have these months here, right? November, October, and September. We're basically assuming those months, which is the opposite of the conclusion, but then we forced a contradiction each time. So since we have contradictions, therefore the conclusion has to be August, okay? Now, how can we apply that in our examples here? or in our basic statement reason tables? Well, let me give you an example. Let's say you're given if Z then R, you're also given P or not R, and you're given not P. How do you prove that not Z is true by using the indirect method? Well, here first we want to draw a statement reason table. So let's do that. Statement reason. Okay. So now, at this point, we want to, according to the definition, assume the opposite of the conclusion. So we know that this is the conclusion, not Z. What's the opposite of that? Well, the opposite is simply Z, okay? Because we're negating the negation of Z. And according to the double negation, it just becomes Z. So that, the reason for that is initial assumption. Okay, now what we want to do is use these premises or givens in conjunction with that Z, okay? So if you look at the givens, we want to use one of the givens that has a Z in it. So we can see that the first given states if Z then R. So let's write that here as a given, because now we can use the initial assumption with the second given, or with the first given in this case. So now we have R as our conclusion. And as you remember, this is actually modus ponens. And again, we want to do the citations of 1, 2. Okay, now we use the first given. Now we want to use another given that has R in it. So for example, we have P or not R. Okay, that is given. And now we can do here is combine step 3 and 4, right? We have P or not R, but it is R. So what happens here, and let me use a different color. You can actually think of this as, you know, this erasing here somehow. And now we have, therefore, P has to be true, okay? So let me erase this really quick. All right, so what's the reason for that? Law of disjunctive inference. Okay, so here we're referring to step 3 and 4. Okay, very good. So now we have another given here. So the other given is not P, okay? So let's think about this. Let me actually write given here. Let's think about this. Is there anything strange about this? Well, yes. If you look at this, and again, I'm going to use a different color, is it possible to have P and not P being true at the same time? Well, it's not possible, because let's think about this. If P is true, then not P should be false, right? But it says here that not P is true, but therefore then P would be false. But in this case, P is true. So that is actually the contradiction here. Contradiction. And that's the thing. We actually just assumed the opposite of the conclusion. We forced a contradiction. Let me underline this here a little better. There you go. We forced a contradiction. Now, if we have a contradiction, what does that actually mean? What can we say about our initial assumption since we have a contradiction? That the initial assumption was false. Therefore, Z, not Z, has to be true. Okay? Now, as a reason here, you want to write if an initial assumption leads to a contradiction, comma, then the initial assumption is false. Okay. And that's basically it. That's how you prove this, okay? And that's how you do an indirect proof. Again, according to definition, always assume the opposite of the conclusion. Use that in conjunction with your givens, and then somehow force a contradiction, okay? Then you know that the initial assumption was false. So let's look at another example, which is actually more challenging at this point. Here we have a few givens, okay? They're all true. We want to prove that S and not P is true. How do we use indirect proof method to prove this? At this point, I encourage you to pause the video, try it out on your own, and then we'll go back to this and go over it, okay? Okay, so let's go over it by using a statement reason table. Obviously, you can first brainstorm. You can do the informal proof if you would like. But I'm going to go ahead and just do the statement reason table. Okay, so for step number 1, we want to state the opposite of the conclusion. Okay, so we're going to write the negation of the entire statement of S and not P. Okay, so I'm going to call this initial assumption. Okay, now for number 2, we can actually now use De Morgan's law and write not S or P. Okay, so we're going to say De Morgan's law here. Referring to step number 1. Okay, now for number 3, now we kind of have to think about this and say, okay, which other given can we use here together with the not S or P? Well, unfortunately, there's no given right now that we can use, but we can do something first with the givens, so we can use whatever we conclude with the second step somehow, okay? So let's first state not W. If not W, then not F. So that's the given. And here we can actually use not W by itself. Okay, so that's also the given. Okay, what I like to do is always cross these out so I know which givens I have used so far. And there's something we can conclude now here, okay? We can say that not F is true. And that again is modus ponens. And now we can say 3, 4. Okay. Now for number 6, we know not F is true. So how can we use that? Well, we can use it with the given not F. If not F, then not E or A. Okay, so let me cross that out. We use that one. And we can now combine it, step 5 and 6, to conclude something else in step 7. That not the quantity of E or A must be true. Okay, and again, this is modus ponens. Now what we can do here, instead of rewriting modus ponens, we can just say same as 5. Say it's the same reason. And again, we refer to step number 5 and 6. Okay, now the most logical thing here is to now again use De Morgan's law and write not E and not A is true. Okay, again, same as 2. And that's just step 7. And what can we do next here? Well, what we can say here, if you look at not E and not A, what can you say about E itself and not A itself? Well, we know that both must be true, right? So what we can say here is that not E is true, okay? As you remember, that is the law of simplification. I'm going to abbreviate it, okay, for step number 8. Okay, so now we know that not E is true. And we can now use the third given here for step number 10 that not E, if not E, then S. Okay, so that's the given. And now we can use modus ponens again to state that S must be true, okay? So again, modus ponens, we can again say same as 5 for step number 9 and 10. Okay, now if you look at this, we can actually use step 2 now. Let me use a different color so you see what I mean here. If you look at step number 2, and if you look at step number 11, okay? Not S or P, it is S, therefore P must be true, right? So let me write this in here, that here we have P is true, okay? Because we know that the not S and S cancel out. So P is true, and as you remember, that is called law of disjunctive inference. And now we say step number 2 and 11. Okay. So at this point, we have one more given left, right? Did we use the third given? Yes. So we're going to use if P then A. Perfect. So we're going to write here if P then A. And again, if you combine 12 and 13, what must be true here? Number 14, that A must be true. Again, that is modus ponens, okay? Let me actually write modus ponens here for steps number 12 and 13, okay? Obviously, you could have just said same as 5, okay? So that's fine. I just wrote modus ponens because it's not visible here on the screen. Okay, so we do have A now here at the end. We still don't have a contradiction. Okay, there's actually something we can do here now to force a contradiction. Look closely at step number 8, okay? We know that not E and not A is true. So as you remember, in a conjunction, in order for a conjunction to be true, both conjuncts must be true, okay? So if you think about this, for step 15, we know that not A must be true, okay? I'm actually referring to step 8 here. And the reason is, again, law of simplification. So we can just write same as number 9, okay? Here we're referring to step number 8. Again, remember how for step 9 we said that not E is true because of step 8, and we said that not A is true in this step 15 because of step 8, okay? Both of conjuncts must be true. Okay, so what do you notice at this point? Well, at this point, there's something going on here, which is a contradiction. And there it is. We did force a contradiction. Okay? Now, since we have a contradiction, what can we say about our initial assumption? Again, as we go back here, we assumed the opposite of the conclusion, not quantity S and not P. Well, therefore, now we can say that the initial assumption is false. So therefore, we can say that S and not P must be true. And the reason, again, if the initial assumption leads to a contradiction, then the assumption is false. So I know this proof was lengthy. It's 16 steps here. The thing is that it was a challenging type of proof, but I think it's still good to look at these types of proofs, okay? So that we're well prepared for the Regents exam. So here's actually a better overview of the entire proof. Everything is nice and typed out. I actually did it a different way in this case. As you can see that here now the contradiction doesn't lie with A and not A. But if you look at steps 11 and 15, I actually contradicted that S and not S are both true. That's a contradiction. Maybe you guys can look at it and see what you think. Because what I'm trying to tell you is that there are different ways to prove the same exact thing, okay? But anyways, this was today's lesson on logical indirect proofs. Again, remember, you assume the opposite of the conclusion, force a contradiction, and therefore the initial assumption is false, okay? Now, if you have any questions, feel free to email me or post a comment to the YouTube video, okay? Otherwise, I hope you enjoyed this video. If you did, please click the like button and don't forget to subscribe. And otherwise, have a great day.